Good afternoon, everyone. I hope you're enjoying your lunch and will continue to enjoy your lunch. Feel free if you need refills to go up and get more. There's plenty of food in the room next door. And continue the conversations we've had so far at the iSEE Congress. Haven't they been very exciting? So my name is Arnab Chakraborty, and I'm a professor of urban and regional planning here at the University of Illinois. It is my privilege today to introduce our afternoon keynote speaker, Dr. Brian Stone. Dr. Stone is an expert in urban environmental planning and design. He researches spatial drivers of urban environmental change with an emphasis on urban-scale climate change. Brian Stone is a professor in the School of City and Regional Planning at the Georgia Institute of Technology. He is also the director of the Urban Climate Lab at Georgia Tech. Brian's research has been sponsored by the National Science Foundation, the U.S. Centers for Disease Control and Prevention, and the Trust for Public Land. And he has been featured in the National Public Radio, the New York Times, and the Washington Post. He is the author of The City and the Coming Climate, Climate Change in the Places We Live, by Cambridge University Press, which received a Choice Outstanding Academic Title Award. Dr. Stone holds an MS in Environmental Management from Duke University and a PhD in City and Regional Planning from Georgia Tech. Today, he will present a talk titled Fires, Floods, and Frappuccinos, Planning for Climate Change in the Age of the Anthropocene. We will hear from him some thoughts on what big cities are focusing on as our population skyrockets at the same time weather becomes more extreme. Please join me in welcoming Brian Stone.
Good afternoon. Fantastic to be here. What an engaging set of topics this morning. I really, the quality and the focus was really fantastic, and I'd love to have the opportunity to round this out. I'm sorry to intervene and impose on your lunch with some notes from Armageddon here. There is plenty of things to be optimistic about. My wife hates this title. She thinks that it's way too grim. But we threw in the Frappuccinos. So I'm going to focus on really a continuum of vulnerability today that ranges from the physical side to the behavioral side, and both of these come together in cities, and both of these can be addressed to some degree through planning and design. And so I'm going to try and highlight those issues for us today and think about planning adaptation. I think this really draws upon a lot of what we've already heard today, and so it really meshes well, and hopefully we'll connect some of these pieces here. I want to trace roughly the relationship between cities and climate over time. We've had kind of a causal area that's switched in the last 100 years or so. Throughout most of our history of human settlement, climate has been the principal driver of where we've located cities, how we've designed cities to be responsive to their local context. In more recent decades, that relationship has really switched, and now cities are rather dramatically driving their climates, have divorced themselves from their climates. And that is both a liability and an opportunity for us. And so we're going to think about that a little bit today. And then moving forward, planning really has an opportunity to be on both sides of this relationship. We're already seeing planning and design as responding to climate-driven challenges, but there's also the potential to actually moderate the climate change itself, to not just be a reactive force, but be proactive. And so I'm going to highlight that a little bit as well. And then we'll have time, I'm sure, for questions at the end, and I welcome your questions. So the context we start with always when we think about climate change are these recent trends and temperature. This is mean global temperature. It's one of my least favorite metrics of climate change because it's so abstract and it's so distant from us. Both the scale of it and the magnitude of it don't really speak to us very much. 1.2 degrees Celsius over 120 years perhaps doesn't sound like a lot. Of course it is. It's measured at the global scale. It's measured across the year as a whole and seasons. It's a terrifically high number. But to appreciate that, you really have to look at a wider time frame. We know here that if you are in this room and you're under the age of 30, you've never experienced a normal climatic year in your life. We've never been within this bounded range of temperature that really defines the Holocene, this most recent geological age. We've been outside of that for quite some while. But you see this gradual curve, and I don't know, it doesn't look so threatening to me. But when we look at it over longer time periods, we see a different set of associations that are a bit worrisome. We can only go back, again, about 100, 120 years with our actual instrument record of temperature. So that's this red line you see here. And then we have these proxies for temperature that we can look at going back deep, deep into time. And they have variable reliability, but they give us general goalposts on what the planet has looked like over time. We can use deep ocean sediment cores, ice cores, entrained bits of the ancient atmosphere in these samples. Give us really the chemical basis we need to roughly assign both a general temperature data point to different periods of time and also the composition of the atmosphere. And so what we see in one hand is somewhat comforting in that, I don't know if this is going to get over there kind of faintly. If we go way back in time, right, back to the Jurassic period that we celebrate with large mammals, the world was much, much warmer. The planet can sustain much higher temperatures and sustain a wonderful amount of biodiversity. That's less of the concern. The concern is the pace here. And so what you see in this slide, right at the origin here, where this is, again, the temperature record, the instrument record intersects this line, we are actually right here. And so you can't see how rapidly temperatures have increased in this last 100 years on this scale against a logarithmic scale. But really what we've seen in the last century is a straight line of increase. And so again, we see higher temperatures over time, but we do not see any evidence that temperatures have increased this fast. And so that is of concern for us. It's a concern for our ecosystems, but even just our basic cities and our infrastructure and how we adapt. What is occurring alongside this rapid rate of temperature increase and really explains it in large extent is the changing composition of the global atmosphere. And the impact of our species really everywhere we look. You can take a spadeful of sample anywhere in the world and see the evidence of us. So whether it's largely detritus of our industrial age, which continues, plastics, fly ash, radionuclides, we can see a very clear soil horizon here, just a few inches down. And we see this again everywhere. You can go out and dig it up in the quad. You can go to Greenland, drill through the ice, and you will find this evidence everywhere. And so what this suggests to us is, like other distinct soil horizons, is that we've seen a transition in the geological epoch in which we are in. I mentioned the Holocene before, which is the last 10 to 12,000 years since the retreat of the last ice age. We now have a new name for the era that we believe we're entering, and that's the Anthropocene. This is proposed as something we've never really seen before as modern humans, and that is to observe the transition from one geological era to another. In that sense, it's scientifically fascinating, but it also suggests the reach of our impact on the planet and the changing context of our life that's happening right now. We really do live in a new environmental era than our parents or grandparents did. And we need to be responding to that in a lot of different ways. One of the ways historically we've responded to climate is just where we've chosen to settle. Early human settlements, post-Neolithic period, we know we're in fertile river valleys, mid-latitudes, places where you had conducive conditions to the domestication of plants, the domestication of animals, and so we find that the early archaeological evidence of human settlement in these zones. So just where we settle, we know has always been very sensitive to the climate, the local climate. We can look at the urban scale and how cities have responded to climate over time. This is a diagram of ancient Beijing. And you can see this clear east-west orientations of the grid about 4,000 or 5,000 years ago. This is something that's repeated by the ancient Greeks and the Romans. And it really affords something that's critically climatic, and that is to be able to orient your structures to a south-facing direction. And so a relatively high-latitude city like Beijing, this passive warming, critically important. And so, there's lots of evidence of more religious bases for this orientation, but a lot of it comes down to climate as well. We see this at the kind of the design of cities at the block scale. And then, of course, down to the building scale, we have a deep tradition of designing our buildings to respond to climate in different ways. The early courtyard housing that evolves in the Jordan River Valley, we still see it throughout the Middle East today, throughout North Africa. It's really just a machine for passive climate control. You have the open courtyard at the center where the tree is in this diagram. You have some kind of a mineral-based stone surface on this courtyard, absorbs that incoming radiation during the day, heats up the air right above it, the air rises, and you get this kind of gentle breeze that flows through the building. You have open windows in the structure, or some kind of a wind tower, which is very common in Islamic design. And it gives you that gradual cooling that wouldn't feel much like us today, wouldn't feel much like mechanical air conditioning today, but it really was a fundamental driver of how buildings related to their local environment and related to one another. We have more recent examples. This is the Dogtrot vernacular design that we find still throughout my region of the country in the southeast. And again, it's taking advantage of these climate responsive principles, these deep overhangs of the house, the central void, the differential in shading, pressure, and temperature, creates that convective movement of air that is just fundamentally climate responsive, and something that we've lost as we've been able to modify our interior climates. And then even early in the planning profession, just our basic codes and regulations of how we structured cities. The earliest comparative zoning in the U.S. in New York, 1916, if I know my planning history well enough, was a response to, again, solar access, technology enabling the skyscrapers, the 20 and 25-story buildings that were creating kind of this inequity for retail in various parts of the city. Where it was seen to be unfavorable if you had a lack of access to sunshine during the day. And so there was an attempt to control the bulk of these buildings, have them step back. If you see the kind of ziggurat structures near the East River in New York, that's a product of this ordinance, this early ordinance and planning. So there's a deep and well-established relationship between climate and cities that flows in one direction, and that is the direction that it flows throughout most of our history of city making, and that is that climate shapes cities, that we respond to it fundamentally and essentially. And that's something that we've lost, but I think we have a real opportunity to return back to. The perfect example of where a climate signature is hard to find is in my beloved hometown of Atlanta, Georgia. We celebrate our soft drinks. We celebrate our sports teams. We do not celebrate climate in Atlanta, Georgia at all. The only evidence of climate response here is that the windows no longer open in these buildings because they don't need to. And so, again, this causal arrow starts to shift. It shifts with the scale of our cities. It shifts with the operation of our cities, but it also shifts with this kind of shutting out considerations of climate in how we design. This is an aerial image of surface temperature in Salt Lake City. It shows a very characteristic pattern that's probably familiar to everybody in here today. It's the urban heat-on effect. And we can see the surface temperature, the reds and the oranges are much more pronounced in the downtown district. And then as we move towards the foothills, it starts to taper off into the drainage areas and the more heavily wooded areas, and we see that natural cooling. And so that differential here between the urban temperature and the rural temperature is pronounced. It's profound. We can measure it across all kinds of cities. It varies during the year, varies based on city size, but we see general rules of thumb of maybe 5 to 10 degrees Fahrenheit on a typical summer afternoon. It can get up to 15 or 20 degrees Fahrenheit. If you live in the suburbs, you have a temperature gauge in your car, you can watch this kind of tick down as you drive home from work. That is both for us, again, it's a major liability for us because it's amplifying the rate at which cities are warming up, but it's also an opportunity because cities really have significant control over the extent to which they're amplifying temperatures. So we have these two phenomena that are driving climate change in cities, most directly through temperature, but it also drives rainfall and flooding. It's the global greenhouse effect, which of course is driving temperature rise everywhere, whether it's urban or rural. And then cities have this unique phenomenon, the urban heat island effect, which are driven by these four, there are other more minor drivers, but four major drivers: the loss of vegetation. We come in after we clear cut, if we're fortunate enough to have forest, natural forest, and we pave over that with impervious surfaces, our roads and our houses. That generates additional heat. Waste heat from our automobiles and our buildings, somewhat overlooked often, but it's a significant variable. There's a ton of waste heat that's emitted from your tailpipes. Combustion remains really very inefficient, and so most of that energy in the gasoline just goes into waste heat into the atmosphere. Same thing with our buildings. Mechanical air conditioning blows in cool air, but it also pipes out the heated air. And so that waste heat at the compressor really can add up in urban environments. In some cities, it's the major driver of the heat island. In Manhattan, Tokyo, really high-density cities, just waste heat is the major driver. But in most North American cities, maybe it's about a third of the phenomenon. But it's a real opportunity for us as we start to think about mitigation and less carbon-intensive sources of energy. We also just need to be thinking about waste heat and how the city contributes to that. And then lastly, urban morphology, this three-dimensional design of the city, is not an easy variable to change. But it is a major driver as far as the radiative forcing that happens in downtown districts, and it is something we can play with over time. So today, cities have become major drivers of climate. And so again, that's a liability and an opportunity. It's been a rapid change. In many respects, cities in the contemporary context are really effective receptacles for water and heat. Designed to throw off water in various ways over several hundred of years. These strategies are now failing us in coastal areas where the storm sewer systems that drain into the ocean no longer drain into the ocean at all times because the ocean is rising. And so we particularly see this, really this time of year, we have annually high tides. We call these the king tides. And so just this is blue sky flooding, right? This is nuisance flooding. There's no rainfall. There's no hurricane in Miami on this day. There's just water that is flowing in reverse in the storm drains from the sea to the streets. And so this is creating obviously a major challenge. We see this in all parts of the world in coastal areas. This is Venice, a city that struggles with sea level rise, but also struggles with subsidence, much like New Orleans in this country. It is not a good time for your city to be sinking as the seas are rising. Heat, of course, is perhaps the most pressing challenge. We've had some really excellent discussion today already on heat, and it's exciting to see planning really inserting itself into this space. It was mentioned before that we really underestimate the threat of heat. We underestimate both the threat of extreme heat and extreme cold, both which remain challenges for us. This is in Delhi in India, where it is not unusual for it simply to be cooler to sleep outside than inside. You know, in an area of the world where it is hot and humid and you don't have air conditioning, this is a pretty common strategy. It's an ancient strategy. Gets so hot these days in times that the asphalt is just literally melting in Indian cities. We've seen this in the U.S. too. We've had airports have to ground all flights because the tarmacs simply were softening and the planes could not move. And so we have a real challenge in front of us in terms of thinking about how do we resurface our cities to be more resilient to temperature in terms of infrastructure, but also how do we make them more resilient for human health. And so returning to this issue of the health implications of temperature, which is really the variable about which we have the most confidence. We can see temperature rising. We know it will continue to rise. Heat, on average, is the deadliest form of weather, so is extreme cold, although I'm not highlighting that here. So in a typical year, tornadoes and hurricanes, we'll have really dramatic events with hurricanes. We've seen this where you'll have many more individuals succumbing to those conditions. But typically, year over year, much less than just succumbing to extreme heat. Even in a single city, as we see here, my city of Atlanta, more people succumb to heat, and we see heat mortality at higher levels than we do from hurricanes, although most people's risk assessment wouldn't place it in that order. We're looking forward, it's not encouraging with what we see by mid-century, really dramatic risk from heat as we move forward, and so adapting cities to these conditions becomes really a paramount challenge. I can show you many examples like this, where I sometimes describe the Royal Guard here as climate pilgrims, in that they find themselves in a fundamentally new world, but they are holding on, really just clinging to the old world traditions, dressing today as if it was 1818 instead of 2018. This is not the uniform you want to wear on a hot day in the spring in London. And so both the drama of the outfit and this young soldier that succumbed to the heat and the protocol that won't allow anybody to address it is, again, it's a real example for me of where we are in this moment, kind of stuck between two eras, living in the era of the new climate, but maintaining that grasp on our old ways. We see it in sports. U.S. Open in 2015. Some of you might remember more retirements than any other major tennis event in history. Jack Sock here, I think, was number 2 in the world. Just couldn't make it through a match in New York. The notion that we can continue to have outdoor athletics in New York in the summer, which is hotter than it's ever been, really begs the question of whether we are assessing risk in concert with a new environmental landscape. Even just our day-to-day activities will not be waylaid by flooding or extreme heat. We are going to have our Frappuccino. We are absolutely going to do this. And so in this case, I call this the age of individual adaptation. This works for a period of time. If you've got a good set of rain galoshes, you can make this work for a period of time. But at some point, the water gets higher than your boots. And that's where we really have to think about more of a collective approach to adaptation. I'm going to see if a related thing here, if this video will play. This is a similar flooding event several years ago in Vienna in Austria, and I find the magnitude of the event is dramatic, but really the reactions to it, I think, are also very telling about where we are in our sense of risk assessment and where we are in terms of our vulnerability that's driven by behavior. I don't know if we're going to get any volume out of this, which is unfortunate. What you can't hear is the videographers, again, in a coffee shop, are typing away on their laptops as this is happening outside the window. First, the car gets washed down the street. Now these individuals are literally, you have a raging torrent of a river flowing outside the cafe, and people are continuing to tap away on their laptops. They're continuing to carry on with their lives. And so, again, there's a physical vulnerability that comes with climate change, but there's also a behavioral vulnerability. And we really find ourselves stuck between these two eras where we're not embracing the new realm. The final example I'll give you is the perfect example because it's from our own country and really could not happen in any other country, I don't think. I wish I could tell you I photoshopped this. I did not. This is an extraordinary decision to make. It suggests a real passion for golf. I appreciate that. But it's not a risk assessment that I would like to see in my own children's decision making. So again, we can think about this in more formal terms, this notion of vulnerability and risk assessment. For much of our era, certainly our era of city making, we've enjoyed greatly a stable climate. And so we have climate variability, of course, year after year, but there's some vulnerability threshold that we're prepared for. We know occasionally we will have extreme weather, we will have hurricanes and tornadoes and heat waves, and we have protocols to prepare for that, and they're not perfect, and people succumb to illness and death. But it's relatively predictable, and we have relatively reasonable response protocols to deal with this. When you shift into a new ecological regime that is characterized by an unstable climate, you must adjust your resilience threshold to account for that. And we do that. We can do that with resilience expanding adaptation. We find ourselves today in a very unwise location. We find ourselves here, well along the road into an unstable climate, but with very little resilience expanding adaptation. We heard some great stories this morning about this. We have wonderful emerging technology to deal with this. We have policy protocols to deal with this, but we really can't argue that we are embracing this challenge anywhere in the U.S. The way we should be. And so I'm going to focus the rest of my talk on what some of those strategies might be. Specifically with respect to heat, they are wonderfully low-tech, wonderfully available to us, wonderfully consistent with a wide set of co-benefits, and slowly starting to enter the bloodstream. So here, I think planning again, we have this opportunity to be on both sides of this phenomenon, the climate phenomenon. We can respond to it, we're having to respond to it, but within cities, we can actually moderate the intensity of the change, and we should grasp that opportunity. So in my research group at Georgia Tech, the Urban Climate Lab was mentioned. One of the principal projects we focus on is simply just measuring how rapidly our cities warming. I started out with that very familiar graphic of how rapidly the planet is warming. Nobody really is measuring how rapidly cities are warming, cities where most of us live by far, and cities where we know we have two climate phenomenon happening simultaneously, the global greenhouse effect and the urban heat island effect. And so we measure this over time, and we're specifically measuring how rapidly are cities warming relative to what's around them. How rapidly is Las Vegas warming relative to rural areas around it? How rapidly is the heat island growing? We care about that because it's the heat island, it's that differential between what's happening in rural areas and what's happening in the cities that we think we can actually control. We think we can at least modify it. And so knowing that number is very important to us. And so the numbers, though, mean a lot to us. What's being presented here is the average decadal rate of change. So Las Vegas is warming at about 1.6 degrees Fahrenheit per decade. That's really, really fast. So we can put the global rate on here just for reference. The global decadal rate of warming. It's a little bit shy of 0.3 of a degree Fahrenheit. So most of the cities we see here are warming at 3 or 4 or 5 times of the planet as a whole. The median U.S. city, large city, is warming at double the rate of a planet. And so that is something that we need to be focused on. I really appreciated that the smart cities talk we just had, the notion of the data we could collect with these smart sensors. I hope, I'm not sure if I saw on the slide, but I hope that one of those sensors is just a thermometer. I hope we start to measure temperature across cities. You'll see why here in a minute. So in the context of heat, which is the universe that my group works in, we know in theory there are some really fundamental things we can do, and there are things that we used to do, but we've just stopped doing them in the modern city because we didn't think that we needed to. We can increase vegetative cover. We saw what's happening in Philadelphia with managing the flooding and the stormwater. I mean, seeing the green infrastructure renderings around Philadelphia makes me more hopeful than anything I can imagine. It really is, it's not simple, it's not cost-free, but it is remarkably effective. If we can clad our cities in green cover, we can really make a big difference. We can also increase the reflectivity of our cities, the albedo. It's an ancient strategy. It's what we've done throughout the Middle East. We can also re-embrace that again here. We're learning slowly that the best way to deal with too much water in cities is to bring in more. We need more water in New Orleans. The Netherlands is a global leader in this. This also has benefits for cooling our cities that we should embrace. So Waste heat, I mentioned that before. Really some very promising strategies we can focus on that both reduce emissions of greenhouse gases and reduce the emissions of heat to the atmosphere. So in theory, there are a lot of things we can do. We even see this increasingly in our empirical data. This is what we call the Georgia Tech Climate Network. It's a very simple thing. It's a network of temperature and humidity sensors across the Georgia Tech campus. It may be the most dense node of temperature sensors in the United States. That's astounding to me because it's not a really remarkable network. We have about maybe 40 sensors in the network now. Really, we should have that on every street corner in Manhattan. We have cameras. We should have temperature sensors because this is just kind of fundamental vital signs for our cities day to day. But what we see here, again, is pretty hopeful. I should note that prior to this, we really only have a handful of temperature monitors around major cities. The airports, some amateur weather stations. City of Atlanta maybe has 10 weather stations across the city. That really is insufficient. And so what it doesn't allow us to do is to see how we have this variability across space with temperature and why we see that. I want to highlight something in particular here. Right here we have two interstate bridges. This is I-75, 85 that comes down through Midtown. Georgia Tech is here to the west of this. This is 10th Street Bridge, the 5th Street Bridge, identical in terms of size, but very different in terms of their heat signatures. And that's because the 5th Street Bridge was redesigned about 8 years ago to be a green roof. And so we can just see with the basic temperature data that if you bring in a pretty modest amount of green space, you can dramatically change temperature in the context of a large city. And so this is what we're interested in working with cities on and have been doing with my group over the last couple of years. So I'm going to highlight a study here that is focused on something that we don't really do in a formal sense today, and that is urban heat management. Can we develop urban heat management plans for cities? Basically, adaptation plans. The first thing you have to do this is to convince a city council that they can control their weather. That is not an easy thing to do. It's very easy it's understandable to take kind of a passive crouch that this is a global phenomenon. There's nothing I can do as a mayor. There's nothing I can do as a city council to actually slow the rate of warming, but that's exactly backwards. Cities are better positioned to slow warming than the international community is. And so we're working with cities to think about what that would look like. And so I'm going to go through some of the work we did in Dallas more recently to get a sense of what this might look like if we were to do it more uniformly across U.S. and global cities. This is just showing these basic trends in Dallas. Dallas is a hot place, we know that. The urban trend is increasing more rapidly than the rural trend. There's a lot of variability here, but the heat island is growing in Dallas. That's well established. I showed you my rankings of cities that were warming rapidly. Dallas was in the top 5 there. To do this work, we come in and I work with colleagues at Georgia Tech to do this. We apply a regional climate model, the weather and research forecasting model. This is a model that we use most typically to develop the 10-day weather forecast. We can also use it to do simulations, and it's most significant for us that it allows us to create a continuous surface of temperature estimates, air temperature estimates across the city. Again, Dallas has 2 airport stations here. They know where the temperature is in maybe 5 places. We need to know where the temperature is across the city. Land surface temperature is wonderful, but it's actually not sufficient for us if we're going to talk about health and how health is driven by climate. Land surface and air temperature don't correlate as consistently as we would like them to, and so we really need to be measuring air temperature or at least simulating it. So here, for every 1/2 kilometer grid cell, we simulate temperature and we get an estimate for every 5 minutes. We do this for historical warm season. So we did this for the 2011 May through September, which was a really hot year in Dallas. So we think that's a proxy for what we'll see moving forward. To drive this, we get to get very geeky with my group, with our land cover data, our geospatial analyses. They have really high quality land cover data sets in Dallas, which made this a fun project. So we have high confidence on where the tree canopy is, where the roads and the buildings are, which we need to drive the climate model. We have a whole range of layers: barren land, water, everything you can think of. And what this produces are maps that look like this. They look familiar to us, but I'm pretty confident you've never seen a map quite like this. This is air temperature. It's 6 feet, 2 meters across a major U.S. city. These are average temperatures, high temperatures and low temperatures for the warm season in 2011. And they show a very characteristic pattern that we believe is there in theory and we can see with our monitoring and our modeling, and that is a tapering heat island that's very intense around the industrial districts here, the major interstate that goes up through here, the areas in red on the left, and then on the right, the low temperature. We're actually more interested from a health perspective in the low temperatures. We know heat risk is maximized at night, and so you can sustain, this is why we can live perfectly comfortably in a desert environment. It cools down dramatically at night, so even if you don't have air conditioning today, that's less feasible. But the ability for the body to cool itself off at night, for your heart rate to dissipate somewhat is really important. And so if you have sustained exposure to heat across a 24-hour period, that's where you really start to get compromised. And so we focus on these lower temperatures at night, which are really high for minimum temperatures, but they're less dramatic. The high temperatures there are fairly remarkable. What this shows here, the areas in red, this is the average high temperature over about 180 days. So Dallas, for about 180 days, pushes 100 in these areas. Again, you wouldn't see that from a single or a handful of weather stations, but when you can disaggregate it this way, you can see additional patterns. The beauty of the model, I should mention that we run it historically. We have the handful of weather stations we have around Dallas. We can see how well the model is performing. This model performs surprisingly well, better than I would have thought. The average error between what we modeled and what we monitored was 0.2 of a degree Fahrenheit. So the model really is performing, at least in the places where we can validate it, it does perform very well. And that's why your weather forecast is as accurate as it is. Now, looking 50, 100 years ahead is a different kind of modeling. So I'm not suggesting that that's without flaw. But looking in the contemporary period, these models are surprisingly accurate. So we can also, with the model, simulate. We can see, well, let's plant trees around Dallas and see what that does for us. That's where it gets most interesting from my perspective in terms of planning policy. There are lots of theoretical studies out there where we just double the tree canopy, we triple the tree canopy, and we say, wow, we cool things down, that's cool. But in the real world, we don't do that. In the real world, we have to leverage the policies we have and the incentives we have to increase green cover, and so we try to do that in our studies. Here we look at ordinances that are already on the books, ordinances that we can look at in other places to get a sense of what's feasible, what could you do if you had a minimum green cover standard for streets and parking lots. They really don't have this in Dallas, but we see it in other places. And so if we adopted these ordinances, what would this do? We adopted a standard of 30%. Sounds, I think, somewhat aggressive, but we know there are very urban environments where we exceed this all the time. Just walk around Brooklyn. Most streets are 80% tree canopy cover. So you can absolutely do this. We find in our simulation that to adopt this policy in Dallas means typically we're increasing tree canopy from current conditions by maybe 10 to 15%. So we think that's feasible. It doesn't happen in 1 year. It takes some time, but we think it's actually quite feasible to increase tree canopy cover by that amount around the city. So we do that, and then we can compare the current conditions to our new environment where we've planted trees and expanded canopy. And you can see it really effectively reduces the hotspots quite dramatically, just with an ancient technology of tree planting that also, by the way, creates a wide range of co-benefits for us. Stormwater, property values, most things we can think of. We can also use just cool materials. It's also a higher tech solution, but it's been around for a long time. You can do something as simple as paint your roof white. That will reflect away that incoming shortwave radiation. It doesn't contribute to more greenhouse warming. It remains in the shortwave part of the spectrum. And so this is something we can do that's effective. We know we have a basis for this in policy. Los Angeles is now mandating this. There are other cities that mandate this, where every time you reshingle your roof, you have to meet a minimum, we call it albedo standard, reflectivity standard. So again, if we look over the period of 10 to 20 years, we could really dramatically increase the reflectivity of our cities by adopting these policies, and I think more cities will do this. So we simulate this, and again, we see really an equivalent amount of cooling that we saw to the green cover. We can combine these two things and look at a final scenario, and it's really dramatic. It almost erases the city. These are not the most aggressive policies one could imagine, but they're very effective. They do need to be uniformly distributed around the city, but they're very effective. And so we want to then ask the next question, which is, well, so we've cooled down the air. What does that do for human health? And so I'll highlight a slide that Zoe highlighted, which is very helpful to us, or a similar slide, at least from the same research group, is that we know how human health responds to temperature. And we know this at individual cities from the surveillance data that's available to us. So we can look, and we know about the cold side, equally important, although the cold risk is dropping year after year. It remains significant, but dropping. The heat risk is rising year after year. And that slope of that, once we get over this 70-degree trough, is very steep. It's very steep. And so every degree increase in temperatures over, call it 70 degrees, comes with some additional risk, and we can see that in the mortality data. We simply look at how many people are dying, not of heat, of all causes, and we can associate that with temperature because it's very hard to tease out the heat signature for mortality. It's usually there's some underlying condition, respiratory, cardiovascular. Often heat-related deaths aren't coded that way, so we just look at how mortality is increasing, and then we can statistically figure out what is the risk of every degree increase in temperature in Dallas on a summer afternoon. We actually don't do that. I say the we, that's too generous to me, but there's some very active groups around the world that are doing this. So we can then generate statistics and say, well, heat mortality in 2011, something we really didn't know at all, we can only measure statistically in a reliable way, shows that about 115 people we think succumb to heat. It's a modeled number, we can't be sure. But that's our best guess. We can then look at what we think is the attributable mortality to the heat island itself, because we know how much hotter these neighborhoods are relative to what's around the city. So we get this UHI attributable mortality, about 53 deaths, we estimate. And then we compare this to other events in Dallas in recent history, a horrible tornado season in 2016, West Nile virus in 2012, and this really is a significant risk. It appears to be the most significant weather-related risk, climate-related risk for Dallas, and that's true with most U.S. cities. So this enables us, really for the first time, to map where mortality is happening around Dallas. Where do we think people are actually dying or were dying in 2011 from this? And it shows us a really useful pattern in the sense of it is not necessarily in the hottest parts of the city. What we see here is here's this Love Field. This is the airport. It's very hot, right? But nobody lives there. And so it's not enough simply to know where are the hot spots in the city. We have to know where do the people live, where do the sensitive populations live, and that gives us a much better sense. We don't do that explicitly here. It's embedded in the data. But we know in these deeply red zones, these have relatively high proportions of elderly population and just high proportions of population. I mean, the heat mortality happens where people live. And so if we want to direct interventions to deal with heat, we need to direct them to places that are both hot and places that are heavily populated and places where we have sensitive populations. This shows essentially the benefit, the offsets. This is the amount of deaths that were avoided in our simulations by having cool materials and trees. We find a number of 20% that we offset. We know that to be too low. And it's too low because of some insufficiencies in the modeling itself. We still are working to get these models to represent tree canopy shading effectively. So we think of this as kind of the minimum benefit we could get, but it's a measurable benefit. And it's a benefit that really can save a significant number of lives, particularly as we look forward to projections of what we think heat mortality will be by mid-century. So our conclusions for this study, we know vegetation and cool materials can literally change the weather in Dallas. We see it day to day in our modeling. We're not just looking at climate, we're looking at weather. We can offset heat mortality through these strategies. There are a range of benefits that we haven't measured here that we think would also flow from this. We find that greening strategies are actually more effective than cool material strategies. And so by a factor of 3. Now that assumes that it's looking at a square meter of new canopy versus a square meter of new cool materials. It's often easier and less expensive to implement cool materials, so that's important to highlight. And then we can give a really specific number. We think Dallas needs to plant 285,000 trees. And we can give you a number for every neighborhood. We think you need to plant 8,500 trees in this neighborhood. And so that is probably the most useful aspect of this study, is that it is targeting our interventions to specific neighborhoods and providing specific numbers. It's also enabling the neighborhoods to see what their individual risk is. It's very effective to have a neighborhood know how they compare to other neighborhoods. It activates them in the political process and enables other kinds of strategies. I've got just a few more slides here. So that's a point I want to hammer home just briefly here, is that part of what's useful about thinking about climate change at the level of cities is it makes it meaningful for residents. Too often we're focused on 2100, we're focused on the polar regions when we talk about climate change. We're talking about variables like mean global temperature that nobody knows how to translate into their own experience. And so this was a wonderful campaign in Vancouver several years ago where they wrapped telephone poles with barnacles to show you what the sea level will be in your neighborhood if nothing happens by the end of the century. Global warming is closer than you think. Really effective strategy, I think. So part of that we see in Louisville, I'll highlight Louisville because it's been a few more years since that study, is that the findings of our analysis are leading to actual changes on the ground in terms of policy. There are a number of rebates now for cool roofing. There's this public campaign, #Cool502. You can share your own climate experiences. You can share what you've done to your own property to make it more heat resilient. It's a small bore effort, but it's really unlike what we've seen in other places, and I think, again, increases that educational component. Louisville, amazingly, is one of the only U.S. cities not to have a tree ordinance. It now does. So that's a good start as far as preserving the tree canopy that's there. So I'm going to conclude with just a few slides, and then we'll take any questions you have for me. The fundamental context in which we live has changed. It's not a future event. It has absolutely changed. We see it in every part of the world. And this really signals to me that the time for adaptation is here, and it really needs to start to influence everything we do in cities. There are limits to individual adaptation. I think the major thrust of adaptation we see today is very resource dependent, and it's individual. We increasingly need to see more collective adaptation. And so I think we are rapidly approaching that time where the rain galoshes are overtopped by the water in your favorite cafe. And so we need to move quickly. Things that melt, things you care about melting. I think this is true. We all like ice cream. Come on. We love Greenland, but we like ice cream more. And so, meaningful adaptation is urban adaptation. It's not that it's in a city, it's adaptation in the places we live. This is what is more likely to activate us, to help us with our risk perception and to engage us in this process than constant invocations to focus on the polar regions. I'm not minimizing that as a threat to us. It is a huge threat. But we really need to localize the threat because it is here with us. This is a slide that was from the Louisville study that I didn't share, but it really shows the synergy we see between these strategies. It's true for heat, but it's also true for flooding. It's true for a range of things, that when we combine these strategies, it's so much more of a powerful effect than any kind of siloed approach. And so I encourage that in adaptation. And then lastly, we're really starting to see a transformation in my own field of planning design. We see it in other fields as well. This is the American Society of Adaptation Professionals. We have an emerging professional field that's focused on climate resilience planning. We have the 100 Resilient Cities. We have really encouraging things that are happening around the United States. And so I'm hoping that will continue to happen and increase its pace. So it has been a total pleasure to be here with you this afternoon. I hope I didn't put a damper on your lunch overly much, and would be thrilled to answer any questions you have for me. Thank you. Thank you.
Thank you, Brian. That was a really informative, thought-provoking speech and a great way to summarize all the sessions we've had, if not since this morning, since 2 days ago. Thank you very much.
Yeah.
We have 2 mics here. Jenny on that side of the room, and I am on this side. Please raise your hands. We'll come over.
Thank you. Thank you so much for a great talk.
Thank you.
What you point out is a lot of different connections, and you ended up with this synergistic approach, but that also speaks to the need for connections of our different fields. And as universities, we haven't exactly been terrifically good at that. And I see that as a challenge. I'll give you one example. A few years ago, the land-grant universities were asked to identify a person among their land-grant staff who would represent them on the climate hubs, and these were regional climate hubs. We belong to the Northeast. We actually, as UDC, were the southernmost university in the Northeast hub. And as we went around the room to see who had been appointed to these climate hub representations, most of them were natural resource people, or folks like myself, ag economists, right? There was only one respiratory scientist who had been identified for that role. And to me, that was really telling, because I don't think we've been terrifically good at connecting across our different fields. And it seems to me, to get to the synergistic thinking, we have to get much, much better at doing that.
Yeah, thank you for your observation. I mean, I completely agree, although I'm encouraged by trends in my own field, I guess. We remain very siloed. The funding mechanisms for too long have been siloed around climate change, for sure. But I think that's changing rapidly. I mean, I really see a renaissance in an interest in urban areas, at least at the federal funding level. And so I'm getting invited to work with folks that I never would have collaborated with before. Because there is such a focus on urban research right now. And so that wonderfully brings in the planners, because we have urban in our name, right? We have city in our name. That's helpful. But it is necessitating so much more collaboration across disciplines. So I'm working with my colleagues in civil engineering more than I ever have. And we see it in our agenda for this morning. I mean, the backgrounds of the speakers this morning have been very diverse. And the ability to see the connections in what we're doing were very clear to me. And so I agree that we have not been well positioned historically to do this, but I think the landscape is really shifting, and I'm encouraged by what I see. But it's a hurdle for us, for sure. Yeah.
Hi, I really appreciate your talk, especially the way that you used scenario analysis with really actionable interventions. My question about that, though, is that both of those interventions are sort of triggered by redevelopment. If you repave a street, it's going to get new trees, or if you're building a new subdivision, it'll have these reflective roofs. Did you consider, or what did you look at sort of community-driven, more smaller scale interventions that might have similar effects without the high sort of capital cost?
Yeah, that's a great question. I mean, I can answer that in a few ways. One, certainly, new development is often what triggers this, but you don't just pull a permit for new development, right? I mean, in many cities, if you're going to re-roof, you got to pull a permit for it. I mean, the city wants its piece, right? So, the way it works in Los Angeles with the albedo ordinance is that when you pull a permit for a re-roofing job, you have to meet the standard of that time. So that's not new development, right? The notion that that's a staged process. So in the instance of cool roofing, it will be a 10 to 20 to 30 year timetable over which we are resurfacing the city, but we are doing it in small ways every day. And so what I think the most valuable contribution planning can offer and kind of city administration can offer is to bring these initiatives into the DNA of the city, which is the codes. Because cities are every day resurfacing themselves, remaking themselves in small ways. And so a lot of the climate initiatives we've seen to date have been large-scale projects that the city has taken on, and it's New York plants 1 million trees. I think that's one of the wonders of the modern world, that New York planted 1 million trees. But that is different than an ongoing process that happens with every little cell in the system. And so Seattle has something called the green factor. It's known generically as a green area ratio policy, and it's minimum green cover that's required at the parcel level. And that really gets to the DNA of the urban system, and I think is the way we need to move. So I think we can do it through the larger strategies, but I think these approaches really can be implemented on a regular basis if we get it into the codes. And then the last piece of this was, I showed the 2 bridges in Atlanta, and you really can do this at the neighborhood level. And so you can do this on your own property if you're fortunate enough to own property. You can measurably reduce temperatures on your own property by implementing these strategies, and I think that's essential for people to see, to engage them in the process. That's a great question. Hi.
Hi, thank you for the talk. Thank you very much. Some of the topics you brought up, I think, really sync with things that are going on locally in our community. Mm-hmm. Some of the topics of tree cover, of plant cover. We have topics of building energy efficiency on our campus and reducing air conditioning, but also we're experimenting with buildings that create chilled water, but then they create hot water at the same time, so they're rejecting their heat instead of to the outside, but into the reheat systems that our buildings ironically use heat in the summer, but that's the way we dehumidify. Yeah. So these are really great things. I think they really wrap up nicely in the talk. Some other topics that have come up recently have to do with solar farms. So everyone has the ability now to, in the next year or so, to buy their solar from local solar farms. So the heat that's rejected through coal plants and natural gas plants, you can offset that heat and that carbon footprint, and that's a pretty awesome thing that's just coming about in the next few months here. It's in the conversation this summer. Mm-hmm. But also I'm curious about another topic that comes up has to do, every time I talk to somebody about putting solar on a farm or in a field, they ask me, why don't we put solar on a parking lot? And my answer is, in Illinois, we have to have you have to drive a snowplow, and you have to get the snowplow with its dump truck sticking up, and you have to build this 5 times more expensive space frame. But has anybody ever looked at maybe taking the top levels of parking garages and turning those into green spaces? Nobody seems to ever park on the top level parking garages, and turning those into pollinator friendly, and maybe just putting solar straight on the ground. I was curious if anybody's ever talked about that.
It's definitely happening. It's definitely happening. I mean, I appreciate your concern about the snow, and so that's not a concern we have in Atlanta. Well, it's a huge concern when it happens, but it didn't happen very much. But we have exactly that. We have solar over parking lots. We have solar on the top deck of parking lots. That's lost economic value for the property owner, so you have to usually provide an incentive. If it's a university, then that's an easier sell. But there's a lot of potential for integrating these strategies. So whether it's PV and cool roofing, I mean, PV systems are interesting because they really need to be as low reflective as possible. They need to absorb every bit of sunshine that falls on them. And while efficiency is improving, they're still remarkably inefficient. I mean, they dump a lot of heat. Solar systems do. So, if rooftop environments are kind of ideal for that because you typically have a heat that's already dumping all that heat anyway, or a rooftop that's already dumping all that heat. But there have been increasing studies focused on integrating cool and PV roofs. And so, I think that's a technological issue that can be resolved. Universities in particular are perfect places to think about this, not only because we have the expertise to be experimental, not only because universities are willing to use themselves as laboratories, but because we have kind of an entrained pedestrian population. I mean, we really do have great exposure on university campuses where people walk from class to class and live on campus, and so it's a natural place to look at these associations. And so, I mean, you're referencing things that are happening in Illinois. I see that on a lot of university campuses, which are well ahead of the cities in terms of their adaptation thinking, for sure.
And also, I was just curious if we could have a round of applause for anybody that would love a vegetarian only option next summer.
I'll clap.
So I had a question about one of your slides. So over here.
I think you're okay.
Yeah.
Hi.
So in your slide about Dallas, you found that the neighborhoods of Dallas which have a higher population are those which suffer from higher air temperature. I'm wondering is there a causality over there that neighborhoods in general which tend to have higher populations because of denser morphology or more anthropogenic heat, do they end up eventually having higher temperatures? And then what are the planning implications of that?
Yeah, that's a great question. One that we probably haven't thought about enough. I mean, what we see in Dallas is that it's not that the hottest areas are also the most populated. In some cases, they are. And there's definitely an association between density and heat. in Dallas and all major cities for the most part. But what we're observing is that the hottest districts are not always the districts that we think should receive the interventions, at least in a prioritized way, because often they're large industrial districts like airports where you don't have much population. And so, historically, the little bit of heat planning we've done has often looked at a heat map for a city and said, we need to focus on the downtown district, for example. Well, in Atlanta, in my city of Atlanta, nobody lives downtown. Very few people live downtown. It's an employment district. And so cities have limited resources. We have to prioritize where we do these investments. And so we think it's very useful to be able to look at this neighborhood by neighborhood and to account both for where the temperatures are high, but where we see the actual heat stress occurring. In general, the more dense urban neighborhoods tend to have the higher heat signatures, but those may not be the most susceptible neighborhoods. We may find that we have higher elderly populations in less dense neighborhoods, and so all those variables need to be factored in. Yeah. Anybody else? Hi.
I had a question about one of your slides. You mentioned people were recognizing the solution to too much water is more water. I wonder if you could say more about that.
Sure, yeah. I mean, that is not my field of expertise, but we see this. There's a big initiative for this in New Orleans. And so part of the issue is in a city like New Orleans is subsidence, right? And so New Orleans is a bowl. We describe it classically as a bowl. It is at a lower elevation than the waters that surround it. It is protected by a set of levee barriers and sea gates, but it's at a lower elevation. And so part of the strategy historically has been to pump out any water that comes into that bowl, right, immediately. That has the effect of drying out the soils, and so that soil profile in New Orleans is described as a sponge. And so as you dry it out, it desiccates, and it compresses, it subsides. And so by having more moisture in the system, you have less subsidence in the New Orleans case, and that actually is a really useful thing. And so what characterizes New Orleans in some respects are their neutral grounds. They're very large medians. If you've been to New Orleans, you've seen this. Many of those are formal canals. And so New Orleans is now working to reestablish those canals to provide a constant source of moisture to keep the soil profile moist and buoyant. And so it's a unique situation in New Orleans. You don't see that in all cities. But we do find that cities are actually able to absorb and retain more water if they have a baseline level of moisture. And so that's one reason that porous paving is a really useful strategy for us. It allows the water to infiltrate into the subsurface, but it keeps that moisturized, and that's really helpful in a lot of respects. And so thinking more creatively, using the science more effectively to understand the range of strategies that work. We don't have great science yet on how incorporating these kind of storm management strategies that employ water cool down cities, but in theory they would. And so that's something that we're focused on now. It's a great question. Hey, how are you?
Fine, thanks for the talk. It was very interesting. A lot of people have commented on the tension among environmentalists between mitigation and adaptation strategies, and especially like the political agenda of one versus the other. The idea that going more to adaptation will tend to take our eye off the ball of reducing the problem. From what I can tell, your urban heat island work may allow us to have our cake and eat it too. That is, perhaps to a certain extent, we can both mitigate and adapt at the same time with these kinds of strategies. That's a hypothesis. Do you agree with it? Do you think the work would bear you out? And then second, if so, are there other areas of intervention that you can identify that also provide wins on both mitigation and adaptation at once?
Yeah, great question, Ralph. So I call it adaptive mitigation, and it is absolutely feasible and compatible with what we're proposing. I mean, perhaps not in every. It's not to suggest that these strategies are the most effective things you could do for mitigation, but there is a lot of synergy between them. And so if you cool down a city in the summer, you cool down the energy demand for air conditioning. That's a major factor. If you are, there's been a somewhat of a tension here around planning and density in general for cities and mitigation and emissions. But generally what we find is if you have a certain baseline level of density, you have the resources to promote things like transit, right? And cycling and other dimensions, other strategies that get us out of our cars. That in and of itself has a benefit for mitigation and reducing the emissions, but it also has a very measurable benefit for reducing waste heat. And so when we account for the fact that probably about a third of our heat islands are from waste heat, anything we do to improve energy efficiency is reducing waste heat. And so there really is a lot of overlap there. And so I don't see that tension between those two strategies. There are strategies we can think about in terms of mitigation that might be carbon sequestration at the site of a power plant. That wouldn't have real clear adaptive benefits if it's outside of a city. You might get some waste heat reduction. So I think we can prioritize mitigation strategies that also have adaptive potential for us. But mostly in what we're talking about in cities, anything that's reducing the energy intensity burden is going to have that benefit too. Yeah. Hi.
Oh, hi. So your focus on the health impacts, I think, is exactly right as a way of communicating with city leaders and the communities. And you look at the vulnerable population to heat stress in terms of the elderly.
Yeah.
And that's fine, but I just suggest that another layer that you might want to look at would be pregnant women. And the studies are strong in terms of the association between heat and premature births and low birth weight. Those often aren't counted.
Right.
I think they're never counted in terms of heat-related mortality, but it might communicate with another segment of the urban population in terms of the benefits of taking on these strategies.
Yeah, it's an excellent observation. You actually have given us too much credit for what we did. And so what we can see, our methods are not so precise at this point that we can tease out that the individuals that succumb to heat here in this district succumb because they were over 65 or because they had diabetes. We can't really tell why it is that the population in this part of the city is succumbing to heat. And so we are probably capturing, in this case, we're looking at heat mortality, but we can also look at morbidity. We can look at heat stress. And so the heat stress that a pregnant woman would experience would absolutely be amplified, and you have a greater level of susceptibility to that. In the methods we would use, we would just be lumping those sensitive populations together, and we can't really tease out how many of these individuals have a pre-existing condition, are pregnant, are over the age of 65. We can't tease that out yet. But I completely agree with you, and what I try to highlight when I give this talk and this question comes up is it is true that we've seen in the epidemiological studies in the aftermath of extreme events like we saw in Europe in 2003, that the vast majority of those who died were elderly. But it is also true that people die in every age cohort. And so sensitivity runs the gamut of age, and we really all bear some vulnerability to this, particularly when we reflect on the fact that as we're seeing temperatures increase, we're seeing more heat exposure, we're also seeing more failures of the grid system. And so, we are now relying on air conditioning and electricity as our principal adaptive mechanism to deal with climate change. When those systems fail in hot weather, that becomes a very dangerous system, and it inverts vulnerability. It's actually those of us that are most well adapted, have the higher resource base to air conditioning that become the most vulnerable because we're not used to high temperatures at night. So it's a great question. Completely agree. We're not actually able to tease out those sensitive populations specifically. I hope we're able to in the future, but vulnerability runs the gamut of the population for sure. That's a good point. Okay, I might have time for one more question. I've got to sneak out and get on an airplane. Anybody?
All right. Thank you, Brian.
Thank you. I really appreciate it. Thank you.
Let me turn it over to Evan for his concluding remarks.
For those of you who I have not had a chance to meet yet, I'm Evan DeLucia, and I'm the Baum Family Director of the Institute for Sustainability, Energy, and Environment. Before I bring our proceedings to a close, I have a brief public service announcement. There will be an opportunity for 8th to 12th grade students to attend the first Champaign-Urbana Youth Sustainability Summit on October 13th at the Siebel Center for Computer Science at the University of Illinois from 9 to 4 p.m. The CU Youth Sustainability Committee has a Facebook page, and you can find some more information about that on their Facebook page. Well, what a fantastic Congress this was. I'm overwhelmed and excited and a lot of emotions right now, but I'm hoping that as you leave us today, you'll leave with some new knowledge and that we've all learned an awful lot, that we're aware of some major uncertainties and that will help us establish a new research agenda. And I've noticed a fair number of business cards being exchanged, that will build some new collaborations and some new friendships from this meeting. Before I get to the acknowledgments, so I'm an ecologist by training, science person. These impressions I want to offer you are personal impressions, just a few of the things that are kind of resonating, cross-cutting things that are kind of resonating in my mind as I reflect on the last 2.5 days. Boy, we have a lot of solutions, a lot of technical solutions at hand, but it was emphasized at several points that policy, regulation, and funding opportunities are kind of getting in the way of implementation. So we saw that with the talk on microgrid technologies. We've got this technology for incorporating renewables now, but there are policy issues and ordinance issues that are kind of getting in the way. Dr. Stone mentioned it, and we've heard repeatedly through this Congress, the issue of de-siloing. Sustainable cities is a grand challenge, and we're not going to solve it in the technical arena, in the social arena, in the economic arena. We've got to come together to work together in a very interdisciplinary context to solve these kinds of challenges. I don't often think in my own research about the social dimensions. I was really excited to hear the term, the meaning of infrastructure. We think about the social science dimensions and landscape as infrastructure and incorporating that into our thinking about how we go forward. There were some contravening challenges that are probably I'm making too much of, but that were kind of fun to think about when we think about the urban environment and the value of trees in the urban environment in terms of solving the heat island issue, and then the contravening issue is if we're going to think about urban food security, trees kind of get in the way of that. So we heard a little bit about that stressor of where you have trees and how you use them. I thought that was kind of interesting. The role of technology was infused through our talk, and the thing that really impressed me, we heard a fantastic talk by AT&T and Microsoft and Bobby about autonomous vehicles. The thing that's startling to me is tomorrow's here today. This is all happening in real time, and so that technology is really upon us. And then just an impression about something that we didn't talk about at all, but that just occurred to me in just thinking about this whole context of cities as we go forward, is cities as a center of global governance. So more and more, cities are becoming more relevant in how we govern ourselves than even our national governments and our state governments. They're setting the tone. And so cities can play a very important role in providing leadership, sustainability leadership as we go forward. So that's certainly not comprehensive. Those are just a few of the cross-cutting issues that I was thinking about as I was reflecting on the last day and a half, 2 days. Okay, a few acknowledgments. We're very fortunate to have support from the Office of Vice Chancellor for Research here at the University of Illinois and the Center for Global Studies at Illinois. Both provide direct financial assistance. Of course, I would be remiss if I didn't acknowledge Joel Friedman and Erica Corneliuson. Joel and Erica manage the Baum Fund, and the Baum Fund provided the initial funding to launch the Institute for Sustainability, Energy, and Environment, and continues to be a good friend of the Institute. Our Congress organizers did a spectacular job, I think you would all agree, under Madhu Khanna's guidance of pulling together an incredible Congress. The Office of Corporate Relationships also is very instrumental in helping us bring in some folks from the private sector and the corporate world to participate in our Congress. This would not happen, these congresses would not happen without the really committed staff in the Institute, and that begins with Jenny Kokini, our managing director. Michael Kenfield was very instrumental in helping us build our connections with the cities and the climate resilience program that you saw. Tony Mancuso is our communications person and is also our IT guy and is running up here all the time to help hopeless people like me who don't know how to run PowerPoint after all these years. Amy Rosenberry is at the front desk and is also very important in kind of keeping everything running, and those embarrassing photos that will be on Facebook and elsewhere, you can thank Jordan Gobig for that, who's been here. So in closing, I want to thank our staff for making this possible, our funders for making this possible, and all of you for participating in making this a fantastic Congress. Give yourselves a round of applause.